Okay, so we are starting our next talk, and the title is a little bit mysterious. It's about, I hope I'm not gonna mess it up, Rubyana Gems and Jesus, I messed it up. Ractorous Rubetta Stones. So, and it's gonna be done by Luis. So please welcome him.
A cold, dark cave. The faintest sound of hammers and chisels plinking away in the distance. A beam of light flashes into the cave as the first chisel breaks through and the darkness scurries away for the first time in centuries. But then the light from the outside is met with a strange new light from the inside. 5 stones, patterns dancing on their surface, begin to glow, the runes shifting and moving constantly. A 6th stone rests beneath them, a single instruction etched into it, this one unmoving. Bring me 5 keys from one cycle of the minute glass. And so I welcome you to Indiana Jones and the Raptors of the Lost Ark. Thank you. Except there are things called lawyers. And these entities talk about intellectual property and lawsuits and millions of dollars in damages. So, welcome to Rubyana Gems and the Ractorous Rubetta Stones. My name is Louis Antonopoulos. I'm a professor of archaeology at Thoughtbot, as you can see. I'm also the recently named co-host of our AI in Focus series live stream, which airs every Friday at noon. So either after a long night at the pub, if you're here, come watch it, but it's also saved on YouTube. A bit about Thoughtbot. We are a design, development, and product agency. You likely know us from our gems, the most popular of which are FactoryBot and FactoryBot Rails. I also wanted to call it, though, a few new gems we've been working on, and I think I was so excited to hear different people talking about LLMs and specifically Ruby LLM. So the 2 gems, sorry, give me 1 second. Actually, this is a good moment. I found when I talk, I get a little excited and my mouth gets really dry. And then I have to drink water. And that is like so boring. For you, it's a little bit anxiety inducing. For me, people on the stream don't want to watch it. So earlier you were an orchestra of music, and today, I'd like you to be, I invite you to be an orchestra of voices. As you can tell, my talk is about languages. So I would like to hear your languages. So when I drink, please, in your native language, call out something like chug, 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 anything at all. Are we ready? Because this is going to happen several times during the talk. Ready? Okay, here we go. Thank you. That is so much better than just me drinking quietly on camera. Okay, so our 2 new gems, Top Secret and Michelle. Top Secret and Top Secret LLM. What they do is they anonymize the text that you're sending to APIs or LLMs, but they do it in a structured way. So the LLM essentially gets like a JSON of, sorry, and I should put the URLs here. So the LLM or the API gets a JSON with like private information essentially constantized, and it deals with that, and then it sends a response, and then you can parse the JSON in return. So if you're concerned about setting things like, so as we talked about in the earlier presentation, like if you're putting in in a form, here's my credit card number, I'd like to place an order, here's where I live, and you don't want to send all that to an LLM where it keeps it, you can use something like Top Secret to anonymize that data in a way that you can still accept the LLM's response back and deal with it in a structured way. And then the other gem I just wanted to bring up was Michelle, which it is a, look at this, right? It is especially tailored for healthcare applications that need self-scheduling capability for users. And I think this came from the CloseKnit project, which several of you in the audience have worked on, and the challenge of trying for a user to self-schedule with a doctor. So just a couple things. Looking at the numbers on Ruby Gems yesterday, we are nearing 1.6 billion downloads. And so I've been pushing a new corporate slogan, Thoughtbot. $50 says we're in your gem file. So help us get to that. And remember, every time you install a ThoughtBot gem, a dog gets a toy and a kitten gets a new ball of yarn. So please, do your part. Okay, back to the talk. We're going to be talking about Ractors, and as we learned on day one, Ractors are really close to JRuby performance. I mean, it's like right there. But now, Charles was talking about millions of things happening. But what? What if we talked about trillions of things happening? That's right, Ractors, JRuby, they're practically the same. So feel free to use this in production. Don't use this in production. All right, let's talk about the challenge. Here are the 5 stones represented in a series of shifting runes. At the end of the talk, we're going to break these ciphers in 60 seconds. So that's what we're building up to. But let's go back to the beginning. When they discovered the Rubetta Stones in a cave beneath a park very close to where we are now, you might even have passed it as you were walking in. Maybe you saw some doorways with some locked gates. When they discovered the stones, I was sitting in my office at the University of Ancient Codes. I was writing an article, this is true, about how using a large language model to break codes was a hopeless cause. I had asked one LLM to create an encrypted message, and then a separate LLM, a separate instance, to write code to break it. And it just failed miserably. And so I wrote, that's why this would never make a good conference talk. But then my phone rang. It was the project lead calling from the Rubetta Stones site a dig site. And as I learned more and more about these stones that had been discovered, I found 4 things. So these 5 stones have been decaying steadily since their discovery. They're covered in different glowing runes that are constantly shifting, rotating their cipher twice a second. If we use a freeze ray, which is real, we all have this, on a stone, it slows the rotation down to once every 5 seconds, but it damages the stones more, so we can't use it a lot. And finally, if we can provide 5 keys from a 1-minute cycle to the keystone, something will happen. So, with this new information, I created a new AI assistant, Rubyana Gems, who publicly goes by the name Anthropic Claude. And I asked Rubyana, can we do it? And Rubyana responded, absolutely. Bring in the Ractors. That's how it happened in my head. The real response, more like this: I'm here to help you dig deep into the mysteries of the Rubetta Stones. Ready to unearth some ancient secrets using the power of Ruby and Ractors? This discovery is going to be absolutely groundbreaking. What treasure shall we excavate first? Thank you, Rubyana. That'll do. Let's get to the code writing and maybe less of the talking. So, we have our challenge. We're going to decrypt 5 rotating ciphers in 60 seconds with Ractors. So, that of course begs the question, what exactly is a Ractor? Does anyone actually in the audience know this? Can you please escort these people from the room urgently? Get them out. I know less than you, so this is not good. Just keep it to yourselves. Okay, a quick summary. A Ractor is a Ruby actor. And so then that begs the question, what is an actor? Well, the actor model is a computation model with an actor as its building block. In response to receiving a message, an actor can make local decisions, create more actors, create more messages. And so actors can modify their own state, but they can only affect others through messaging, removing the need for locks and synchronization. So the Ractor model, which you can read about here, and here I'll reference the lightning talk from yesterday, read the effing manual. And I promise you, I read every word of the URL. So the Ractor model, which you can read about in these 2 pages, is Ruby's actor model abstraction. It provides parallel execution without thread safety concerns, and object sharing is limited. Unlike threads, Ractors cannot access the objects in other Ractors. So before we get to code breaking, let's try to understand them a little bit technically. And we're going to go through about like 5 or 6 like small code examples so you can understand how to use them. And then we'll get to code breaking. Okay, so first of all, thing to note, a Ractor must be called in a block. If you just say excavator equals Ractor.new, it throws an exception. Cool, we'll create it in a block, it can be empty. But when you run this, you get 2 different outputs, one from Ruby 3.4, one from 4.0, a message that was updated just back in December. Ractor is experimental, and the behavior may change in future versions of Ruby. Also, there are many implementation issues. In the commit on December 11th, I found this message was changed, but there were no other code changes. So I think it was kind of a marketing thing. It's like, there are not really that many implementation issues. I think it's fine. It's just a little bit experimental. Anyway, if you don't want to see either of these warnings every time you use a Ractor, all you have to do is this. Warning experimental is false. And now it's quiet. Thank goodness. Cool. So now we run excavator Ractor.new, and there is no warning. All right. The common Ractor pattern. These are the methods we're talking about. Send, receive, then we do some work, then we return a value, and call take. We're going to look at a couple of variants of this, but this pattern here, send, receive, take, we're going to go over about 4 or 5 times with comments so you can see it. So let's look at a single Ractor. The example here, or the analogy here would be a single archaeologist in the desert digging for runes. So we create a new Ractor, and on line 2, we say site equals Ractor.receive. And that method blocks until send. So this thing is running, and it's just sitting there on that receive line. After it gets unblocked, then it's going to do some work. In this case, it's going to scan for the R rune, count how many of them are there, and whatever that last line is, like all Ruby, that's its return value. Cool. So we then call excavator.send, and we send it anything we want, some parameters. And that unblocks the receive. So it goes from line 2 to line 3, it does the work and returns it. But that line then, or the next line here on line 7, artifacts found as excavator take, that blocks until the Ractor returns. So you don't have to worry about from the time on line 5 when you say send, if it finishes the work before you ask for it, or if it's still working, like that take isn't going to get it early or late, it's going to get the value that comes back from the Ractor. And now let's practice again. Are we ready? Perfect. And we get our output. We excavated 2 runes from the dig site. All right, that's one archaeologist. Let's look now at multiple archaeologists. So our example here is there are 3 archaeologists. They go out on a bus. They go to different dig sites. The bus waits for them. They get back on the bus before we come back and find out what runes did they discover. Same pattern. So we're going to create 3 Ractors in a loop on line 1. We're going to explicitly specify a parameter for our Ractor.new on line 2. And you'll notice that I'm heavily shadowing the site number. It's a little bit for visual understanding. But also just to note, if you say Ractor new site number, do, and you don't say do site number, you said just do site, and inside that Ractor, you tried to call site number, you tried to access it, it would throw an error. So we have to take the data that's coming from the outside and essentially re-give it to the Ractor on the inside. So again, on line 3, we call receive. That blocks until send. Then we're going to sleep on line 4 to mimic some amount of excavation time. We're going to look at the length of the dig site. And here we're going to return some JSON with some data back, a site number, the number of artifacts we found, and how long it took. So on line 9, we have some data that we're going to pass into it. And so for each excavator, we're going to send it one of those 3 pieces of runes. Again, that send unblocks the receive. The Ractor does its work, returns JSON, which we take on line 13. And important note here, now this blocks until all the Ractors return. So this is the bus waiting at the site for all the archaeologists to get back on board. And then finally, we'll show our output. So what this looks like when you run it is we get our start time, and then in order, we found 13 characters in 3 seconds. Site 1, that archaeologist took 10 seconds, and the third one took 5 seconds. But until we printed our output, so that first line there, that doesn't even appear for 10 seconds because it's waiting for all of them, and then we get all our data at the end. So that's not always helpful. Let's look at a slightly different method called select. And in this example, so I'm going to just go back one. In this example, this would be like, we're going to, let's see, right. In this one, the archaeologists are all working nearby. So they're just going to a site and digging, and as soon as they find something, they call out and they say, I got it, I got it. And so we can get their return value early from excavator number 2, while excavator 5, let's say, still digging for runes. So we create our 3 excavators. The setup is pretty much the same. We dig for a random amount of time, and we sleep. And then line 5 blocks until send, and it's also the return. So here I've sort of combined the Ractor.receive with the actual return value. You can do that. You could also separate it on 2 lines. I probably would, but for the sake of the slide, I tried to squish it a little. On line 8, we have the dig sites that we're going to pass to our Ractors. And then for each one, we're sending them one of those pieces. Again, that call to send unblocks the receive, and it does the work and returns our value. But now, on line 13, we're going to call Ractor.select on our excavators. And so the result of that is we're going to get those responses as they come back. So when we look at the output, we can see site 1 responded with its work in 3 seconds. Site 0 responded in 4, and site 2 responded in 5. So this is a helpful way to get information as it happens. Just a couple more of these, and then we'll get to the fun part. A streaming Ractor. So in our first example, the Ractor did some work and exited. But what if we have a Ractor that we just want to keep around, and we just want to keep, it's going to keep doing work? So this is what I called the streaming Ractor. We create our Ractor, a single Ractor. We call receive, which blocks until send. We do our sleep. And then on line 5, we call Ractor.yield with some value. And so what that says is return a value, but don't wait. So this one is just counting the number of runes there you see on line 3. So when it's done counting them, then it's going to return on line 7, excavation complete. We call it the same way. We send it a piece of work. In this case, a single piece of work. And then we're going to loop over it. So we're going to call excavator.take. And note, so this is line 12. This blocks until a Ractor yields a value or exits. So we don't have to wait for all of them to finish like we did with the bus example. We're going to get them as they happen. And so this is our output. We can see that each one takes a slightly different amount of time, and as it goes through the work, we're getting our output. It found an artifact, etc., until it's all done. Next, we're going to do conditional Ractors. What if we had a Ractor and we wanted to do different work? So in this one, it's the same setup as we saw earlier, but now on line 4, we just have a case statement. And so here, we're doing different work based on some condition. In the example, it's a site number. Maybe it's some part of your data that you're looking at. But then we could say, go do different work. So we don't have to say, like, I don't know, if we were parsing user emails and then we were like validating emails and then doing some other thing. We don't have to create 3 Ractors. We can just have 1 Ractor that sits there and like does stuff for us. So on each excavator, we call excavator.send, and we send it work. And then we're going to call map and call take, and that's going to block until the Ractor returns. And so it's basically going to fire it off, and we're just going to get it back. So 1 Ractor did 3 different kinds of work. 1 counted characters, 1 searched for runes, 1 searched for unique runes. Okay, last example, this is the cool one. A tiny Ruby, I totally failed on how to explain this. It was boggling my mind, so I rewrote it. It's a pipeline. Okay, so we create a Ractor. This is an excavator. So it takes from the runes, it sleeps for a couple seconds, and then it digs up a random rune and covers it in dirt, because that's what happens when you dig up runes. Note it is calling yield here, so it's not doing anything. It's waiting for someone to take. So now we have a cleaner. The cleaner takes as a parameter an excavator, and it yields to the excavator, and it takes, and then G-subs on it. So basically, it's going to take whatever comes in, it's going to clean off the dirt, and then it's going to say, hey, excavator, I have something for you. But again, it can't work yet because it's yielding on line 6. So now we have a cataloger. And a cataloger just says, hey, I found a rune at this time. This also has a yield, so it's also not going to run until something happens. And this is where the magic is. We have a puts on line 11, and then 5 times on line 12, we puts cataloger take. So when we call cataloger take, line 9 frees up, and that Ractor says, cool, I'm ready to show the log of when this was found, but it's like, oh wait, I need the cleaner to clean it first. So that unblocks the cleaner on line 5. The cleaner says, cool, I can proceed now. Wait, I'm blocked too. I need to give this to the excavator, passes it to the excavator. Now the excavator is unblocked. The excavator says, here's a random room in dirt. Then the cleaner continues, cleans off the dirt, then passes that, or essentially the cataloger then pulls that and says, we have found a clean rune. And so when we look at it, it takes a varying amount of time, and it's doing this work over and over again. So I don't know exactly how you might use this in a real world app, but I wanted to give you an example of sort of like what it feels like to work with Ractors, because it's a little bit weird, right? Send, receive, take, yield, select, so many things. But hopefully if you decide to explore them more, you'll know. Okay, one last thing. The most common Ractor error is you do something like this, which seems like a reasonable thing to do, but this will immediately error because you cannot access non-shareable objects, in this case, in a simple hash, by the non-main Ractor, and so it's like, blah, can't use it. So you could pass it in, like we did in some others, or you could just freeze it. This lets the Ractors know that it's not going to change out from under you, and it guarantees that no one's going to try and use it. So this is totally fine. We freeze our hash, we can use it inside our Ractor, no problem. The other way, with another piece of documentation whose URL I read fully, we can call the make shareable method. And so this has some parameters. You can do like, I don't know, deep freezing and not deep freezing. Things happen. If you're interested, go read about it. It's fascinating, I'm sure. In any case, if you're just playing around with Ractors, and you're like, how do I get this thing working? Either freeze it or call make shareable. Okay, we know a lot about Ractors. Now we need to talk about cryptography. Okay. The cryptography we're about to break that was very sad. Please more next time. Okay, we're going to use a simple substitution cipher. This is the easiest cipher in the world to break. It's just like one letter is mapped to another one. So if we had the word conference, it might become that word because we map every C to a Q, every O to an L, etc. If we change that mapping, if we map C to A or O to some other letter, it's going to look like a totally different word. And so this is like one of the earliest ciphers that I think civilizations used to like encrypt messages. Very easy for modern computers to break. But as a benefit, it can be broken quickly. So as I was like thinking about, I don't think I want to run a 2-hour process to see if it works in a half-hour conference talk. So we're using substitution ciphers. In our case, A to Z are going to map to a different rune. So we have an alphabet of runes, and we're just going to map an English letter to one of these runes at random. That's our cipher. This mapping is what's constantly rotating in the slide that you saw before. So how do we break it? I'm sure there are libraries that do this. I didn't want to do that. I wanted the experience of working with Rubyana Gems, working with Claude, to explore like, hey, could you actually write decryption code if you didn't know much about decryption? It was really fun. We got there. It was a really long journey. So many times it would say like, no, this will work. And I would run it and it would just be gibberish. I'm like, that did not work. There was a lot of work here. Finally, I got to a system that worked, a generalized solution for breaking substitution ciphers. And this is what it does. First of all, we use the count of each rune to map the most common cipher letters to the most common letters in English. So this phrase, Eteo in Shurdlu, is like one of the many, there's like a few different variations, like most common letters used in English sentences. So if that first rune appears the most, maybe that's an E. And if the next most frequent rune, well, maybe that's a T. And so You basically apply that first one, and you probably are going to get out garbage because it's not going to match exactly. But maybe you hit a couple letters along the way. So what do you do with that? You're like, well, I kind of guessed right. You can't just keep guessing arbitrarily. You'll never find it. What you can use is a tool I found called quadgram scoring. And a quadgram is just a list of 4 letters. It's like, I don't know, it's many, many thousands of lines long. 389,000. What it is an objective measure of how English is this phrase without knowing English. And how it works is like this. 389,000 lines of this. And you have patterns like TION at the very top, 13 million, we'll just call them points. Going down a little bit, INAN and SINC, that's like 1.3 million is the score that it gets. GSCI and DOSS, that's like 7,000 points. And at the bottom, AAEY and AACX, which is the last entry, 1 point. So what happens is you take your phrase, you've thrown a random decryption at it, and you get something back. And so then you score each 4-letter chunk against this list. And if you score really high, if you find TION, you are really close to a solution because that pattern appears a lot in the English language. And AAEY appears nearly never. So you're like, that wasn't the code. Keep going. Again, that's only the one cycle. So what we next do is, so we've scored it. We have a value. And now maybe we swap 2 letters. Maybe we swap the first rune for E and the second rune, etc. And then we have to decide, do we keep the swap? So in general, if the swapped letters lead to a higher quadgram score, it means you probably made some progress. You're closer to English than you were before. But sometimes you can go down a bad path. You can actually make something that scores higher, but isn't the right key. So to not get locked down this like false path that will never lead you to the actual decryption, periodically you swap and you try a worse score to see if maybe that leads to a better final outcome. And then you keep swapping and keep swapping and keep swapping. And then the last part of this is what I call the chill. And so we decrease the temperature over time so that a regression where we had like a worse score and we're like, yeah, let's try that worse score. The more time goes by, let's not accept those bad swaps as frequently. Like early on while we're investigating, let's explore a lot of things. And as we get closer to the end, we're running out of time. We don't want to try bad paths now. We just want to see like, will this path lead us to a decryption? And so we have a better chance to converge on the actual solution. And then we just keep going. We keep swapping and scoring until the score threshold is reached or time runs out. So I got that working, and I was able to feed it a random encryption cipher, and it would take some amount of time, and it would break it. I'm like, cool. Now I'm going to do it with Ractors. And I really thought I reached the end of the line. Yeah, because the Ractors were slower. And I'm like, oh, crap. That's going to make a terrible conference talk. How can I talk about Raptors if they can't even outperform a single thread? So I tried a lot of different things. I looked at like the performance of them starting up. I looked at like how I was allocating them, all kinds of crazy things. And what I finally got to, though, were a few different breakthroughs. One, and this is akin to the example that we looked at where the Ractor had a case statement and it was doing different things inside itself, right? One was counting runes, one was counting unique runes. So let's have each Ractor use a different starting point. Maybe one uses the English frequency key, where E is the most popular. Maybe one kind of randomizes that a little bit. Another one just picks a random frequency of letters altogether as its starting point. A reverse frequency key. Like there's so many different ways you can do this and basically say, since we have, X number of cores working on this, let's have each one do different work because we don't have a lot of time. So we want to kind of like blanket the landscape and cover every possibility so that we're not all putting our weight in. Like if E is not going to be the starting point, what if we didn't even start there? So this started to give results, and the Ractors started catching up to not Ractors. And then the second part was having each reactor use an increasingly aggressive cooling strategy. So where I was saying before, like, hey, maybe we explore these alternate paths where we accept a worse score. So we let the first group of reactors do that. And then the last group of reactors were like, no, pretty much just stick to it. If it's a bad swap, don't do it. And that way, we again sort of maximize our chances of one of them finding the true path through. This might be the last drink. So let's see. Thank you, thank you. All right. We've come now to the final moment, the moment that has been waiting for us in the darkness, in the cave, waiting for us to break the cipher. Now, here's the thing. A substitution cipher, we actually know what it says. Like, you could freeze frame this, decrypt it, and find out what it is. So, what these messages actually are messages from an interview with Matz, who is a famous archaeologist. And this was from an interview. I wanted to see these messages. I found them inspirational over and over as I was breaking the cipher. So you can scan through it. It's all from one interview. And I just thought this would be like a really nice thing to break. So cool. We know what the messages are, but our challenge is not to decrypt them. It is to find 5 keys in 60 seconds so that we don't have an infinite amount of time. So when I run the demo, we're going to try 4 ways to break it. We're going to try it with a single thread. We're going to try it single thread with our freeze ray that slows down that rotating cipher. We're going to try it with Ractors. We're going to try it with Ractors with a freeze ray. I gave him the laptop for 30 seconds. Got into the presentation. I can't believe it. We're not doing that last one. We're not doing it. Charles, if you're watching out there. All right, let's do this. Let's do our demo. Can everyone see that okay? Actually, let me, it is rendering weirdly at the moment. There we go. Okay, cool. So, I'm gonna spin this around. Thank you for that tip. So, here are our ciphers. They're rotating twice a second. And so, if I say go, it's gonna try breaking them. And actually, I'm sorry, I do have to go back down a little bit. This is gonna get weird. Actually, it's okay, it's fine. It's not getting anywhere. You can see on the right, like for the current message, maybe it's getting up to 20 or 30%, maybe a little bit more. Never gonna find it in time. So let's try with a freeze ray on. Let's give the process 5 seconds for each one to break through. And so here in the middle, I've introduced a new element here that shows how long until the next cipher rotates. We have our 5 seconds. And again, what percent decrypted is the current block? And it's trying. I think it'll get higher. It might get to like 60 or 70% of a message. But again, it just doesn't have enough time to try all those different permutations before its time runs out. And just to be clear, this is a live demo. This is not recorded or anything. The overall thing failed twice at Tiny Ruby before we got it through. So this is real. All right, let's give up on not Ractors. Let's try now. We'll turn Ractors on. We'll leave the freeze ray off. And so it's getting some higher numbers. I'm seeing periodic 60 or 70%, which is pretty remarkable that it's trying to go through all those, it's going through all the permutations, testing quadgrams, scoring it, trying different paths over and over again, each Ractor doing different things. Still not enough time. So it's damaging to the stones, but we're gonna have to use the freeze ray. We're gonna turn on the Ractors, and we're gonna go. And so like I said, might fail a couple times. Sometimes it solves it really early. This is the exciting part. It's actually the only time in a demo when I've like wanted it to fail. That builds a little drama. But let's see what happens. Let's go, Ractors. All right, we're on the first message, already through. We got 55 seconds, that is a great start. It has cracked the second cipher as well. We're on the third stone now, 97.4. Oh no, it lost it. Those are the frustrating, when you see those really high numbers, or like a 99.8, and then it runs out of time and it cycles it. It is, you're like, come on. It's like one letter. And it just keeps going through it. And it was interesting because I tried with this to be like, look, I have a 97% message. Can I send it to an LLM, have it evaluate it locally, and come back and say, it's probably this letter you want to swap? Couldn't do it. I'll tell you about that later. Talk to me. We're at 18 seconds, 2 messages left. Let's see what happens. All right, we've got it. 13, 12, 11. We did it! Yes! All right. Fantastic. And now we can take our keys and we can give them to the keystone. Another message. Let's hit that one with a freeze ray blast. All right. What's this going to have? Did I hit decrypt? Not yet. Is it going to be money? Power? Release date for Skyrim 2? Who knows? All right, let's see. We're at the keystone, the final step. All right, it's working through it. We're taking extra care here because we don't want to get a false message from the keystone. So we're gonna slow this down a little bit. I think I'm only using fewer Ractors for this one. Starting to come clear. Oh no. Oh no. Oh no. It was a warning. Ractor API is experimental and may change in future versions of Ruby. That was a journey. All right. I want to leave you with 3 thoughts. First of all, Ractors are experimental, still marked as such in Ruby 4, although we saw the reduced warning message. So there's hope. There's also, I saw a message that they're hopeful that in Ruby 4.1, it will no longer be experimental. So this would be great news for people who love Ractors. The second thing I want to leave you with is learning about code breaking while working with an LLM was very fun and fulfilling, and really a multi-month journey of getting that demo to work and learning about cryptography on the way. And the last thing I wanted to share is that I feel so lucky that I get to work with a language as beautiful as Ruby and with Rubyists as lovely as you. Thank you so much.
I must say it was a really good plot twist with this key that we discovered. Okay, any questions? You really want me to do my cardio?
Thank you for the talk. In JRuby, when I can
I'm sorry,
build,
please leave.
I can build desktop GUI apps
Yeah.
and have a thread spin in the background and, for example, compute the Mandelbrot fractal or do some report calculations or stuff like that. And then in the foreground, without getting blocked, I can display progress in the GUI.
Sure.
I tried that with Ractor and it didn't work because it blocks and I have to wait for it before it's done. Are there any Ractors that are fire and forget?
So I'm not sure about the full answer. And again, this actually highlights one of the dangers of vibe coding, which is that if you don't fully understand what it's doing, you're kind of at a loss, and it multiplies that lack of ignorance. So I didn't know about cryptography. So while I could look for like code quality and things, it was hard to understand how things were happening. And also I was new on my Ractor journey. So understanding the Ractors themselves, also kind of a weak point. I just knew that they've been interesting to me for so long. So to directly answer your question, I have no idea. The way I think I got it to work was that they were using messages to pass back to like the main Ractor that was saying, cool, this Ractor has found something, everybody else shut down, like don't keep working, we're about to start working on the next one. So I did have like a main Ractor that was listening to messages, and that's how we get the progress that we saw, where it was getting all the messages and deciding among them what was the largest the largest percentage decryption I've received so far. And so that's how like that part of the UI was going, where it was showing the progress of each one. And then for the letters, like it was just, I think, picking one of them and showing like what it's trying, what the English translation of the runes was. So I'm not exactly sure for your case, but I think through messaging is maybe the answer.
Okay, I'll look into it because according to the code you showed us, it seemed like the answer is no. And to me,
might
that
very well
defeats
be.
the point of Ractors. Like, I wouldn't want to use them in a desktop GUI app if they cannot accomplish what I need. But I'll keep following the Ractors feature
Okay.
in Ruby. Thank you.
Absolutely.
Okay, any other questions? Remember, we are inclusive, so it can be about JRuby. I'll get back to you.
Thank you for your talk.
Thank you.
Are there any practical limits to the number of Ractors that you can have running at the same time?
You say practical limits to the number of Ractors? Yes, I actually found, so I think this is a 10-core machine. I actually found I couldn't run 10. For whatever reason, like the performance was worse. So I think I settled on 7 as running it. So I think it's system dependent. Not sure what would happen if you tried to run more than the number of cores, but I think it wouldn't do a thing. So I think there are some limits.
Thanks for the talk. It's kind of not really related, but I really need to know how you change the font size in the terminal. Like, is that possible? Like,
Yeah, absolutely. You mean the part where the bottom part was
yeah,
large?
yeah.
Yes. So since I gave the talk at Tiny Ruby, one of the pieces of feedback I got was that it was really hard to read the timer because it was in the same text as the other, just plain text. And so I worked on the talk for months in the last 7 days. And literally last night, I'm sorry I could not be with you at the after party. Yes, I found out a way to make that large because it was very hard to see. And so at the risk of, let's see, let's cancel that. Let's see if I can bring, You know what? Actually, this is probably a better question for later. Come talk to me. There is a way.
Sure,
I
no
have an
problem.
answer. It wasn't very hard. I can show you the diff.
I need to see it. Thanks.
Watch out for the invoice. Thank you very much, Luis. No, thank you. One more?
One more?
Oh, okay. Sorry. Wait.
Right here. All good.
Thanks, Luis. Great talk. So we know Ractors are experimental in Ruby. That's been reiterated. But is the implementation modeled on something in another language, or what's the inspiration?
I certainly don't have the answer to that, but I think the team that was working on it, my understanding, is just they wanted to try to bring parallelism to Ruby, and this was like one way to do it. So, I mean, modeled on the actor model, but I don't know if like a specific language was like, let's use that language's like approach. There you go. Can we try that again? Ask me the question. We can cut this, right? It comes from Erlang. I have it on solid authority.
He can get it done. Okay, thank you very much, Luis.
Thank you all.